I was kidding. Like, they think
Okay, you should know that this lecture is cursed. So I taught it 3 times already, and I haven't a single good recording of it yet. 1 year it was without audio. Another year, for some reason, it only recorded this part of the screen. A third year, I didn't share the screen, so there's my speech going through the thing. So I'm very excited to see what's going to happen today. Good. So today, I know it's been a long drudge through the matching pennies because we needed to build up some skills. And what we're going to do today is finally moving to a different model. So we're going to discuss Bayesian models of cognition modeled using Bayesian models, right? And so, very brief recap to the approach that we've taken so far, and time for questions if you want. And then we will sort of flip the way that we approach models. Before we took a task and we tried to figure out how would we build a model of agents that solve that task. Today, we're going to do the opposite stance. We're going to take basic cognitive principles and then, in particular, Bayes' rule, and then see how does this describe participants' behaviors across a bunch of different tasks. We're going to see how Bayes rules cognition in perception and belief formation, how it's being used, very briefly, to describe certain aspects of neuropsychiatric conditions. And then we will get to coding, because what you will have to do tomorrow, is take the kind of approach and model that we've been discussing today and apply it to a new task. So, recap, we started from a concrete task, the matching pennies. We developed models of agents solving the task with reference to more general cognitive processes. We learn how to simulate them in R, implement them in Stan for inference. And we thought through and implemented a rigorous Bayesian workflow to understand probably what we, through the model, are doing. Right? And that touches upon the key notions that are part of several Bayesian workflows. If you want a full picture of even more involved Bayesian workflows, there was a paper in the recommended readings called Bayesian Workflow, surprisingly enough. That's actually been turned into a book because they have just a hard time getting it through as a one-paper thing. We looked at prior predictions. We looked at model failing inequality, market chains, divergences, energy. We looked at prior posterior updates, posterior predictions. We looked at parameter recovery, and very, very briefly to model recovery. Are there aspects here that are not clear of the general approach that we've taken? Good. Are there lingering questions and doubts about why we're doing this? So the whole model quality check so far makes sense. It's annoying, I know, but it makes sense, right? Good. Did you have a...
It's just the matching pennies game. Is it used in like, is it used a lot in research, or is it just because you get, it's a good simple model to get introduced to modeling, but is it also used, I don't know.
Okay, so yes, the question for the people on Zoom is the matching plan a good representation of the kind of tasks or of the specific tasks that are used in research, whatever that is. So first is, yes, it is a good example of a task in the class of economic games, which you've probably been exposed to, The Prisoner's Dilemma, blah, blah. They're actually really the same underlying task with different payoff methods. Did you cover them in social and cultural dynamics? Yes, right. So in that sense, it's actually very used both in behavioral economics, in cognitive psychology, and it's also used increasingly in computational psychiatry. The specific of the matching pennies with that, specific payoff metrics in which I win if you lose and so on and so forth, it's been used in a bunch of different papers. I didn't know if it's the most frequent one, but it is a good example also because we can play it with each other and that's fun to start with. But if you had the prisoner dilemma, right, it's just a different payoff metrics. Of course, the cognitive strategies that we might employ in that case might be a bit different because human beings are complex, right? So just a subtle change in the framing might change the cognitive process that we put to play, at least the surface level. But the general process that we did of trying to figure out how would we solve this game, how does it make sense, is exactly the same. And now we're doing the complementary approach that is, what if we already have a theory of how cognition works? Which I'm always a bit ambivalent, right? Because being very ambitious with a theory of cognition is a good way of sort of seeing how far you can push it. On the other hand, as we will see when we will discuss Bayesian pathologies, right? It always feels very caricatural to take one principle and think that it can explain everything. Free energy principle. Yes, it always feels to me like you're doing a Ptolemaic operation where you're just adding epicycles on epicycles on epicycle just to make it sure that it fits whatever you want it to fit. I'm more of a, let's have many models, right? Good. So, Bayesian models of cognition, just as a disclaimer, this is a very, so we're going to cover Bayesian models of cognition in 3 weeks. So we cannot cover the whole complexity that this approach has generated. There is a recently published book, which is free online, called Bayesian Models of Perception and Action and Introduction, that does actually a very in-depth work at introducing very specific models of how the visual system and the cortical aspects that underlie the visual processing, and also something on action planning, but really mostly about visual systems, is working and how to model it. So Bayes' rule, what does it mean to say that cognition is a Bayesian process? Let's go back for a second to Bayes' rule. This is Bayes' theorem. We've seen it a bit, right? What's this? The probability of A given B. What is that? Yes. Exactly. The probability of, start from here, the probability of A. Yes. Yes. Before we see B, right? What is the baseline probability of A happening? The probability of B given A? Yes. The probability of B?
Standardizing term.
Yes, it's the unholy denominator, which we really don't like, and that requires integrals to solve. But it's the probability a priori of the data when not knowing the parameter values, in a sense. Yes. So prior, how likely is explanation X or A before we see the data? Likelihood, how likely is the data given the explanation X or the parameter value A or the combination of parameter values A in the model? Model 1, right? The posterior, how likely is the explanation X or parameter value given the data and the prior? And then the probability of the data independently of the explanation, which is useful to transform back whatever came out of the multiplication in the numerator on a space that sums up to 1, right? Probability space. I mean, this is a very typical representation where we have a prior in blue and the likelihood in red, which is not completely matching the prior, and a posterior that is somewhat in the middle and more pointy, and it has learned. So I stole this from Google image search. If you were running these models, what would you say about the relation between the prior and the likelihood? Think of it in terms of prior posterior update checks. Yes. Yes, that if we are trying to model the data without constraining it too much, the prior is problematic. It might still describe the way that cognition works because we might start with a very wrong idea, right? But from a model fitting perspective, we should be aware of that. Good. So, Bayes' theorem, as we are showing it here, it's often characterized as the rational or optimal way of integrating some prior information taken at face value with some data information, the likelihood, as filtered through the model, blah, blah, taken at face value, into one optimal picture of the world, the posterior. Yes.
How come you can show the likelihood of the density on the same scale as prior posterior? Isn't it a probability function over different things? So the prior is probability over different model parameters values, and then likelihood is likelihood different.
Well,
Search data.
so here we're assuming that we're on a one-dimensional. So it's a model with one parameter. Let's say our random bias agent. And we have a prior for the tendency to pick right, which we can put on this scale. And then we have how many times, right, the agent actually chose right out of how many trials, which gives us a shade, right? So let's say that this is 0.8, whatever. We will have that if the agent has used 8 out of 10, we will have certain distribution. If it has chosen 80 out of 100, it will have the same mean, but a much more pointed, a much more peaked likelihood, right? So if we make this assumption that we're working on a simple one parameter model, we can put everything on the same plot. So in Hamiltonian Monte Carlo, it doesn't make too much sense, but if we were doing a Gibbs sampling process like you've done in decision making, the Gibbs sampling process assumes that the different dimensions can be sampled independently from each other. So you would be able to say, well, we're fitting a reinforcement learning model. Let's look first at the learning rate on its own. And you can sample the likelihood of the data given that learning rate without really paying too much attention on the tau inverse message. And in that case, you would still be able to do that. In the Hamiltonian Monte Carlo, you sample all the parameters at the same time, so it makes less sense because these is going to have one shape with a specific value of tau and a different shape with a different value of tau. Right. Good, and I hope no Gibbs sampling expert is checking the YouTube videos because I really haven't spent enough time with Gibbs. Okay, so we have that, and we've seen so far how Bayes' theorem allows us to do model fitting and parameter estimation. Right? That's been the big chunk of this course, but also methods for. So we have certain likelihood, a prior, model evidence, blah, blah, blah. We can do that sort of things, and we figure out how to get the posteriors that we like. But it can also be taken as the model of a computation as performed by the mind, brain. Luckily, this is not like philosophy of cognitive science, so I don't need to go a bit too much into that. But there's a prior knowledge of the word that we have about what happens, that we've learned. We have a likelihood, like the incoming sensory stimulus in the word or the incoming information. And we have the probability of getting that kind of information, no matter which parameter value we're looking at, which expectations we have, which again is one of the big issues. How does the brain/mind do? But that's a different thing. And that gives us our perceptual experience of the word. Right, so we have a belief in us that we're perceiving something, which is given by combining two sources of information. Yes, okay, I switched some things around. Good. So I'll give you an example of perception in a few slides, because last night it felt very intuitive to put them after. Now we're going to see how it works in practice. So this is a typical experiment, a very, very typical experiment in computational psychiatry and cognitive psychology, because everybody learns Bayes by looking at folia urns, urns containing marbles of two different colors. And therefore, when the cognitive psychologists need to define tasks to test how Bayesian is the cognition and perception of participants in the lab, they just go back to the example they had in their statistics book. And the task is to guess, if we were to sample at random from this urn, what color will the marble be? We have two sources of evidence, right? A prior, where we know from the factory that 2/3 of urns just like this contain more red balls than green balls. Huh? What, sorry?
So you're saying that this one is more red?
No, they're saying that urns like this, like, so the factory puts a little snippet there and said, when we produce urns and we sample them at random, we can see that 2/3 of the urns contain, we're not going to tell you what this one contains, but that's some prior information, right? 2/3, or on a 0 to 1 scale, 0.6666666, right? Or alternatively, right, we got Ingve to try it for us, and he sampled it, and it says, well, I actually took 3 marbles out, and 2 of them were red. So we have a prior that contains some information. Then we have the likelihood, right? What we do is we put our hand in the urn, we extract 3 marbles, and 2 out of 3 are red. So we can combine the two sources of evidence in order to not ignore what Ingve has said, right, or what the factory has put in, and our experience of the word, right? And what would be your conclusion? Right? Is the next marble going to be red or green? Two-thirds red, 2/3 red, red, right? It makes sense that we would be even more confident that the next one is red by combining the two sources of information. But how much should we be confident? Right. So here is a way of using binomial likelihoods to calculate that in a rigorous way. So what we say is we say, given the prior, right, 2 out of 3 are red, what is the probability that there's 0 red marbles in the urn? Right? We ask, and it says 0 chances because 2 out of 3 were red. Ingve said. What is if we had 1 out of 10 of the marbles were red, kind of rate within the urn? This is the probability. And then we draw the distribution, right? Then we take our likelihood, our data, our own sampling, and we do the same. And lo and behold, they're exactly the same, right? Because it's exactly the same information in this specific example. But when we put them together, this is what we get. Do you see any difference? Yes.
With more people.
Yes, exactly. So the mean is exactly the same because 2/3 and 2/3. But now we shrank away probability that the occurrence, the frequency of red marbles is low in the urn, right? Because we keep getting a lot of red marbles. How did I do it here? Well, here I did it like the simple way, where I said, here it was 2 out of 3, 2 out of 3, and here I said 4 out of 6. I combined the information. Right? So this is how Bayes' theorem works, right? It takes 2 sources of information and it combines them, right? Taking them at face value. There's different ways of solving this problem, right? If you check the tree of marbles in the Statistical Rethinking Handbook, I think it's chapter 4 or something like that, you get both the analytical and the counting solution. But here is a way of visualizing what's going on, right? The idea is that while our point estimate of the underlying probability of red hasn't changed, it's still roughly 0.66, right? 2/3 of the marbles in the urn are red. Our confidence in the next marble being red has increased. There is less probability density below 0.5. Therefore, an agent following a Bayesian rule will be more likely to say that the next marble is going to be red. This has been operationalized and simplified as the simple Bayes model, which relies on our beloved log odds. So the idea that the logit of the posterior is equal to the logit of the well, whatever, it doesn't matter the order. The prior plus the logit of the likelihood. Or that the logit of the posterior is equal to the logit of the first source of information, whatever it is, plus the logit of the second source of information. Now, one of you might, or you might start wondering, wait a second, right? We had Bayes' rule that was multiplying probabilities. Why are we summing things up? Yes? Because we're in log space, the log of odds, but it's still a log space. And so a log odds that is below 0.5 of a probability that is below 0.5 is going to be a negative number. So it's going to drag our guess towards guessing green. the log odds of probability that is above 0.5, it's going to be positive, and it's going to drag our choice towards picking a red marble, right? Now you're starting to see why we spend so much time with log odds, because they make life much easier and they just keep popping up all over the place. Yes.
Just to be sure, so here you took the logic for each side of the equal sign, but
Yes.
target takes the log. Just
Yes. Yeah. So this is not exactly Bayes' theorem. It's operationalized and simplified. So it's a specific way of applying the Bayes' theorem to a wide variety of ways in which we perceive and cognize the world. One of the reasons for which, for instance, it's a bit different is that we don't want to have to deal with these standardizing term beneath. Right? We're ignoring that. So what we have here is that the logit of the posterior is equal to the logit of the prior, 0.66, plus the logit of the likelihood, plus 0.66. We do logit of 0.66, it gives us 0.69. We do the logit of 0.66, it gives us 0.69. We sum them up, we get 1.386. Do we? We got shouldn't we get 1.38?
I guess there's some decimals.
Yeah. Yeah, yes. I think I've simplified this to a decimal. Then we do the inverse logit in order to get the probability in the posterior. The inverse logit of 1.386 is 0.8. So a really crucial thing to understand in this way of modeling, right, is that often we think, what is our estimate of the probability? What is our estimate, of the proportion of red marbles in the urn? And if we sum two sources of information, Ingve's gossip on the urn and my own sampling of the urn, we should still think, right, that there is a 2/3 of red marbles in the urn. Right? What we're getting here is not the optimal estimate of the frequency of marbles in the urn. It's the optimal estimates of how often we should guess right. So it conflates the rate and the precision in a sense. The direction is about the rate at which red marbles happen within the urn, and the precision is how uncertain we are on that. It collapses the two. So if we're very uncertain, we still have quite some belief or information that there might still be chances that the right rate is below 0.5, we shouldn't be very confident. We shouldn't pick red all the time. But even if we believe that there is 51% of red marbles in the urn, but we're very confident about that, because Ingve has been very thorough and it has sampled 1 million times that urn, then we should always guess red. So the simple Bayes model is conflating our estimate of the underlying occurrence of red and our confidence in that. Does that make sense? Good. Because that's one of the things that, at least as I've been teaching these models of cognition, Bayesian models of cognition, that's the thing that usually trips people.
Can I ask?
Yes.
Is there a more what does the 0.8 mean, right? It's because it's bounded by 0 and 1,
Yes.
this number, right?
It's a yeah.
But, and it's clear that, higher number means larger, confidence or larger, but what's the difference between, like, what does it mean, like the 0.8 part, like the exact, like, is it a percent, like, is it an expected outcome?
It's out of, if we assume that there is no noise in decision making per se, it's the probability that the agent will pick right.
Under the assumption.
Not right, sorry, red. Yes.
Given that they are a perfect Bayesian
agent.
Okay, but that's just from the definition of how we made the equations governing that decision.
Yeah. So if we assume that humans are rational Bayesian agents under this simplification, presented with this information, 2/3 and 2/3, they should guess right. Or not right, red 80% of the time.
Yeah, but maybe I'm just realizing I'm not a Bayesian agent, but if I observe 4 out of 6, I mean, and I want to maximize my output, I would just pick red all the time. Like,
yes.
Until I learn something else, right? Obviously, but there's no reason for me to, roll a die and decide when I have a majority of observations pointing in one direction.
Yes. So what you could do, right, to model that behavior is you could have a softmax put on top of the of this, of the posterior, and say no what is called no exploration, right? Just exploit.
Yeah.
So very low inverse temperature. And then you would get a very steep decision boundary.
Yeah.
Right. Does that make sense? Yes.
I feel like part of the confusion for this example is that usually you would have the agent pick a marble and then after every new marble update the evidence.
Yeah.
So you have an iterative process, because it doesn't make sense for you to just see free and then take a lump sum of your evidence and then use that to make a prediction for the next free.
But you could have an example where you observe 4 out of 6, and then you're told you have to make decisions about the 100 next marbles. I would just say all of them are red, and that would maximize my expected outcome.
Yeah.
With that's the case where I cannot update it, but I would still I wouldn't say 80%. I wouldn't, for each of them guess randomly with 80% chance that it's red. I would just say they're all red.
Yes. Yeah, and that's where the decision rule can be separated from these models, right? If you want a model that is less reductive, that maintains both an estimate of the underlying frequency of marbles in the urn and the precision of that estimate, there is chapter 3 in that book, or next lecture, Peravade is going to come and teach about the hierarchical Gaussian filter, which is also trying to keep the two aspects separated. You had a question?
Actually, maybe this way.
Okay. Yeah, I know it's counterintuitive, right?
Yeah, it is.
It is counterintuitive, but that's why we need to sort of go into the literature, start from Bayes' theorem and see how Bayes' theorem would see things, and say, how has these been converted in the literature into models? What are the assumptions that these models are doing? And sort of build from there. If we don't like these assumptions, we can change the assumption and make a different model. Yeah. Yes.
In the last results of 1.8.
Yes.
Does that
0.8 or
Yeah.
1.3? Yeah.
0.8. Does that incorporate the uncertainty about the next marble being red? So if before we had a probability distribution, now we just have a single estimate.
Yeah, because here you would have it would need to be like 0.67, right?
Yeah.
Because if you have Ingves as 0.67 and your experience is at 0.67, you should just be here, right? It shouldn't change your estimate of the rate, the underlying rate.
Okay.
But, yeah, but given that now you're actually more pointing, like more of your probability is pointing towards a majority of red. More of the distribution.
But where is that information about how narrow is the distribution?
Well, it's here.
Yes.
And that number there is simply inflating, is conflating how confident you are and on which side you are of the 0.5 divide.
I think if I understand the question correct, like in these equations here, there's no information about the amount of marbles that are drawn. You just have 0.66. And in the plots you show, you have these, the binomial distribution, like 2 out of 3
Yeah.
versus 4 out of 6. So in these equations, there's no information about how reliable or how much information is each source.
No, you're right.
This is just
Yeah.
finding the mode, I guess.
Yes.
And determining the mode is going to be at 0.8, but not the width.
Yeah, I'm not sure because the mode is still going to be at 0.69.
Yeah.
Yeah. It's actually just conflating both. It's making a mess, right? But basically it's saying the more evidence you have that there is more red marbles in the urn, no matter how much more marble there is, the more likely you should be to guess that the next marble is going to be red. It's why is this model so stupid? Because it's very convenient, right? Because it's very easy to implement it and generalize it to a bunch of tasks. Should you be satisfied with that? Of course not. We should do better. But this is how we build up our understanding of how Bayesian models of cognition are conceptualized. This is a first step. We'll do soon a second step, and then we'll build up from there, right? Does this describe cognition? Well, this is a classic example, yes?
Sorry, I don't know how to show you this to change the size, but maybe you could like underline them or circle them and say that the 0.66 probabilities are like estimates of the rate of red, and the 0.8 probability is the probability of choosing red.
Okay, yeah, so you would like that on the slides instead of
Yes.
just oral, yes.
Is the probability of choosing red the next time? Or is it a constant?
Well, so if so it depends on what the task is. If the task is one shots, it doesn't make a difference, right? But if, because the constant or the next time are exactly the same.
Yeah.
But if it's a learning paradigm where you sample from the urn, you make a guess, you get feedback, you sample again, right? You get feedback, blah, blah, blah. Then it's your probability of picking red the next time. And then in the next round, what you're gonna have is you have a budget of 0.8, which is your prior.
Yeah.
Plus the logic of, let's say that this time you got only one red out of 3, 0.33, right? And you would get a new posterior.
Okay, yeah.
And that would be, I don't know, I'm not calculating that right now.
That's it.
Would that be 1 out of 3 or would that be 3 out of 6? Because you have, before you have picked, what is it, 2 out of 3?
Yes,
And then you picked 3 more, as I understand, you've got 1 out of 3.
yes,
So you have actually picked 6 in total.
yes.
So it would be, wouldn't be 0.5. Because
But
that first information is already
In the prior.
Yes.
Okay.
So because you're updating
The likelihood is updated. So like, yeah, okay. So
So
it's only for the next.
the likelihood updates the prior into the posterior. The posterior becomes the prior for the next task. You get data from the feedback, from the sampling, and that allows you to update what before was the posterior and now it's the prior into a new posterior.
Amazing.
Yes.
Perfect, thanks.
To be honest, I have to admit that most of the papers, especially in the early days of computational psychiatry, they were trying to remove learning because it made the model harder to fit. But yes. Okay. So you know this visual display? What do you see there? There's some red marbles that right. So there's discs with color, but we tend to see them as I always going inside. Can't remember. Is that concave? Right. And why do we tend to see them as concave? Yes, Laura.
Because we have an assumption that light comes from above.
Yeah, because we have strong experience of the word of the light coming from above, right? So we integrate prior information into our perception. And this kind of illusion has actually been a really big topic of discussion in the early cognitive science literature, for instance, with people like Fodor saying, oh, right, since we cannot change the visual illusions that we perceive, no matter what we know, perception is different from cognition. Right? And then people trying to show how you can actually train people to see visual illusions differently, or how different cultures that have different ways of life and different architecture might perceive illusions differently, blah, blah, blah. And there's been a big debate about how much perception and cognition are the same. From or not, from a Bayesian perspective, they should undergo exactly the same kind of processes. Right? Where we have an internal model of the word at any given time that's already there, which is our prior. We get some proximal stimulations from the external word, and they get combined with the prior into our perception. And if we want to be fancy, right, given our expectations and initial perceptions, then we act in the word, moving our eyes or listening more carefully or yelling, "Who's there?" Right? In order to get additional information that we can combine with our prior information, which was the posterior from a moment before, into a new percept of the word or representation of the word as we go up in the cognition ladder, right? So our experience is a blend of prior and likelihood. There's a recent book by Andy Clark, The Experience Machine, that tries to make that case very persuasively. The idea is that the word is rich, right? Proximal stimulation can be generated by many possible models, right? So many different things in the word can generate the same kind of visual information that reaches the retina. And priors can regularize our perception to a stable, broadly repeating word, right? As we move around, the information that we get changes, but we still perceive the same person there. The idea is that our previous knowledge of the word and consolidating posterior stabilize our perception. This is one way of looking at that. The complementary way is that at the same time, our imagination is rich, right? There's many possible words in our head, right? And the proximal stimulation can help us making our perception or thought more regular and boring. And this is, in a sense, one of the theories of dreams, right? That dreams can be sort of labile and fledgling and it's unstable, exactly because you don't get the continuous regularization that the proximal sensations are doing, right? So combining the prior and the likelihood, combining our expectations and the information from the word, we can sort of stabilize our phenomenal word. When these goes wrong, so the theory is trying to argue, we might have, if we want to be hardcore, certain neuropsychiatric conditions. If we want to be a bit more pragmatic, we can explain in that way some aspects of certain neuropsychiatric conditions. For instance, there is a whole line of research into autistic perception with the idea that maybe autistic participants are just getting more information from the word or putting a bigger weight on the information from the word, which sort of overcomes and gives them a lot of prediction error on their expectations. They cannot ignore even minimal discrepancies between their expectations and the information from the word, which quickly overwhelms them, right? Sensory overload. Or we have patients with schizophrenia that in certain studies are shown not to have priors. Or to, well, that's a wrong thing, but to put a very big weight on the likelihood, creating these impulsive behaviors known as jumping to conclusions. In other studies, they are expected to have two strong priors. So no matter the evidence that you get from the word, you're still very persuaded that the helicopter is following you, right? And you can see even from these examples, right, that on the one hand, it's a very seductive way of explaining certain things. On the other hand, it's unlikely to explain the big variety of manifestations of neuropsychiatric condition. Okay, just one last point, and then we'll take the break. That Bayes' rule, in as much as it is simply a mathematical formula, both in its original formulation and in the simplified simple Bayes, doesn't care really about the labels prior and likelihood, doesn't care about the kind of information that is within those two terms, as long as it's information. So in that sense, right, it can as well describe prior and sensory stimulation, so expectation and sensory stimulation, as it can describe two different sources of information. Let's say audiovisual integration, right? What you get from your ears and what you get from your eyes, what you get from your haptic sense, right? Your hands, and what you get from your vision. Doesn't really make a difference for the model. It's a way to optimally integrate information, right? And so this is the very last thing, and I should take it off my headphones if I can. Can I do that?
Have a look at this. What do you hear?
Ba, 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 ba.
But look what happens when we change the picture.
Ba, 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 ba.
So this is called the McGurk effect, which is a very prominent phenomenon in linguistics. phonology, the idea is that the very same sound accompanied by different lip movements is perceived as different. This is another case in which we can see how the Bayesian paradigm can be used to understand how these phenomena happens. Why is that changing our perception? Well, it's changing our perception because our perception is not processing just the ba, 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 but it's integrating information that we get from the auditory channel and from the visual channel, right? Plus priors. So if you're a Spanish speaker, right, ba, ba, ba might sound very similar to va, 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 right, because of your prior expectations about things. And with that, we'll take a 10 minutes break. Okay, we should start again. Last few people are coming in. But so the idea is that just like we can generalize from prior and likelihood to a multiplicity of sensory modalities, we can also use it to describe other aspects of our experience, which is the fact that we are deeply social beings, right? So, as I said, Bayes' rule doesn't really care about the nature of the sources. And as human beings, we are continuously learning from our social context, but we continuously supplement our experience of the world via social information, the world in which we are born, both in its physical structures and in its the way that we learn how to focus on different aspects and what to expect is deeply shaped by social information. So the world is vast, our imagination even more, but other people constrain the domain of possible explanations. They give us traditions on how to do things, how to perceive things, how to talk about things, right? You have sounds, right? That creaks in the night under your bed. And of course, your parents will tell you, well, it's not cracking in the wall, it's a monster under your bed or in the wall. And that shapes what you will expect sounds to mean for quite a long time. Social experience, of course, is not just on social experience. Social information is not there just to constrain possible explanations of the word, right? It's also to create different explanations of the word. But if we keep with the general framework, the way in which our perception and experience of the word stabilizes is through the matching of these many different underspecified words or underspecified sources of information. And so there's a bunch of papers where we try to take this idea seriously in trying to explain how maybe the Bayesian pathologies, as some people would call them, are not as much in or only in the way that prior and likelihood expectations and sensory stimulations are merged, but also in the way in which social information is taken into account. And so here there's a bunch of papers. I'm not going to go through them, but basically showing that implicit use of social information in schizophrenia might be weighted more than your individual experience. So you're influenced more by others, even when not asked to take that into account. But when you ask others, or you ask patients with schizophrenia to take others into account, the social information would be downweighted. This is a very simplistic story. It's not going to hold up all over the place, but it is an initial pattern that can be seen. Okay. As Bayes' rule doesn't care about the source of information, it doesn't care about the number of sources of information. So in a sense, we can just as equally have individual experience and social experience as we can have individual experience, social experience from individual one, social experience from individual. So from our perspective, it makes no difference to do the logit of source information 1 plus the logit of source of information 2 and simply keep on adding. Why? Because if we have the posterior is equal to the prior plus the likelihood, when we worked on this logout scale, and in the next, so O at time 1 is going to be equal to the prior, which is the posterior before, plus the new likelihood, like 1. This is equivalent to say that the posterior at time 1 is equal to the prior at time 0 plus the likelihood at time 0 plus the likelihood at time 1, right? When we're working on with additions, right? Logit PDX given A plus logit of PDX given B is equivalent to the posterior here. And as the posterior in the next trial or in the next moment becomes the prior and is added to a new likelihood, right, we can just unfold and say we're keeping them into account all at the same time. Okay, I think that's what we have is that each source of information in the simple Bayes is optimally combined that is taken at face value. And that's where we want to start breaking it now. Right? How rational is really Bayes' rule? Given the ecology of information in which we live. Right? Should you always trust all sources equally? Right? If we take the social thing, right? Should you always trust the same way the idiot that used to teach method 3, that was me, or the impressive teacher of advanced cognitive models? Right? Is it rational to put the same weight on the two people? Or, you know, a doctor that tells you you should get a vaccine, or your friends from primary school on Facebook who says vaccines makes your kid autistic, right? Yes. Should you trust your visual perception the same way when it's a sunny day like now or when it's really foggy? It doesn't make sense to put the same weight on the sources of information. So, and actually there is a lot of literature on how humans are wary, so skeptical social learners. There is a really good chapter in Alberto Acerbi's book, Cultural Evolution in the Digital Age, that sort of reviews all the evidence that should also make us skeptical about misinformation as the biggest threat to our civilization, because in a lot of contexts, humans are actually quite skeptical. They only accept misinformation when it's in their own interest, maybe short term, maybe, just to avoid cognitive dissonance, but it's not because we just suck in social information without a filter, right? So we want to move from simple to weighted Bayes. So how do we integrate weights to that equation? Yes.
So prepare the spoiler on the previous slide.
Yes.
You multiply with the weight.
Well, so if you think that there's really nothing but a logistic regression in a sense, right, we can simply add a coefficient. Right? Now we're just taking the information at face value. When we have a weighted Bayes, we just put a beta coefficient and we call it W because now it looks like a fancy equation. It's nothing but a logistic regression with the outcome still on the logistic scale. And then we can start wondering, right? In a logistic regression, all sort of values for the coefficients are possible, but maybe given the kind of conceptual framework that we have, we should constrain the weights to make sense, right? On a space that makes sense for us, right? So for instance, we could say that it makes sense to take sources of information into account in a space that goes from no consideration, right? We don't care about that specific source of information, we're ignoring it, to we take it at face value, right? Putting some boundaries. Are those the only logical possibilities in the word? Of course not, right? We could do the opposite of what a source of information tells you, right? If you've all been teenagers when your parents told you to do something. Or, we might go above full consideration, right? So say, oh, that person said, well, I'm not sure, maybe, I don't know, the Beatles are cooler than the Rolling Stones. And then you overweight and say, yes, the Beatles are really the coolest. I'm not using bands from my youth because then I feel old. So I'm just using very, very old stuff. But we can say that given the model that we're building now step by step, we can constrain the weights, like doing the opposite doesn't seem to fit our way of thinking about perception, right? So if you think that, if you get some information from the outside that there's likely a tree where you're walking, you're not just thinking very hard, no, if I have information that there is a tree where I'm going to walk, there's definitely not going to be a tree and keep on walking, right? And putting it at 1 because we're conceptualizing this as a step beyond the simple Bayes, right? We simply want to be able to downscale some sort of information. And we'll see how to do that in code in a bit. I also need to make a nerdy note that in the course notes, you'll see a different implementation of the weights as well on top of this. This is a very direct use of the logistic regression framework. And it's very good at describing data. It's very good at parameter recovery. It's very intuitive once you've learned how to think in terms of logistic regressions. But there are several papers out there that are actually considering a different mathematical formats of the weight, in which the way that the source and the weight are combined is passed through a function, which is the log of the weight times the exponentiation of the likelihood plus 1 minus the weight divided 1 minus the weight times the exponentiation of the likelihood plus the weight. And I've spent, and I had multi-spend too much time trying to figure out this one a few years ago. And it sort of makes sense, but really when you start doing simulations, which is my way of understanding things. This is the difference in predictions or the correlation in predictions as you use weights that are on the fancy scale I can't remember which, in the y-axis and weights on the logistic scale on the x-axis, and there's very little difference, right? As you increase the evidence for one in your source of information and pass it through the logistic weight, this is how your outcome changes. This is your outcome. And it's just, there's very little change. But since that's something that I've also used in papers, and that is in a few papers out there, it's also in the course notes, so you can see how it's implemented. Okay, so the weighted base can work as a general framework to describe a bunch of different experiments. So here is an example, very inspired by the Polia urn that I was showing before. In this experiment, you have an urn, you sample from the urn, you see out of 8, how many are red and how many are green. You also see 4 other people who are undergoing the same task. They're computer simulated, they're not real people, but that's not specifically front-loaded. And you can see what they guess the next marble is going to be, the color that the next marble is going to be. And in particular, they can show, well, I'm very confident that it's going to be green. I'm not as confident, but it's probably going to be green. I'm not that confident, but it's probably going to be red. I'm very confident it's going to be red, right? So each of the 4 people is going to give that kind of response. This experimental setup is made such as every trial is a new urn. So you cannot learn, to keep things simple. The outcome follows a binomial distribution, right? You can guess red or guess green. That's the task, right? And what we can do is we can write it as the logit of rate, right? The probability of picking red is equal to, we could put a bias if people have a bias to pick green or red, plus however we conceptualize the evidence from self as a function of the weight, or in a function with the weight. For self, the evidence from the first one weighted by the weight for others, the evidence for the second one weighted by the weight for others, the evidence for the third one as weighted by the weight for other, the evidence for the third one as weighted by the weight for others. So if you've gone through some of Carsten Olsen's experiments, I don't know, but he works a lot on trusted and untrusted advisors. And therefore, in his models, you need to put separate weights on each of these other experts, source of information. In this specific case, the person, Daniel Michael John Campbell, who designed the task, worked really hard to remove any source of learning for the participants, which means that the people that you see playing the game with you, they change at every trial, just like the urn. So there is no reason to assume that they have different weights, that you as a participant will have different weights for different people. And even if you had, for instance, because you think that women are much more confident at picking green or red, right? The model would really have little material to estimate that, right? Because the people change every time. Yes.
why design an experiment with not like to actual real world phenomena such as learning or memory?
Because, excellent question. So a lot of the traditional way of doing things in experimental psychology is to take the theory and implement that in a very controlled experimental design, which removes the need for complex modeling. Right? So a lot of ingenuity has gone into create very complex experimental paradigms so that you can run an ANOVA on them. To characterize it a bit. And so if your theory is about the different ways of weighting social information that patients with schizophrenia in this case have, then you want to remove learning as much as possible from using the experimental setup, because that would only be a confound and would need to be modeled, and it's hard to model. Now we have better computational models, right? And we're getting better at using them. So it would be an obvious follow-up. Carson's line of research is doing that a lot, actually modeling how the weighting of social information is also a function of learning, so that how reliable that information proves to be over time. So, but that's the why it's not been done there, right? Because there's been these very orthogonal development where experimental psychology was trying really hard to draw the consequences of the theory in the experimental setup, and mathematical psychology was trying to draw the consequences of the theory in the computational modeling, and they weren't really talking to each other. Good. So how, given this setup, can we go into something that can be modeled on the log odds scale? Well, we have 8 marbles, and we have a certain number of marbles out of that which can be read, and that is very easily thought of as a proportion, right? Or a number between 0 and 1. With a twist. If you have 8 marbles and all 8 of them are green, the proportion of red marbles is 0. What's the logit of 0? Minus infinite. If you put minus infinite in any equation, it's going to crash. So what we could do, well, there's 2 strategies. One, that's the strategy that we used in that paper, and that is very common. That is, well, we sort of edge it so that 0 out of 8 is going to be something like 0.1. And 8 out of 8 is going to be something like 0.9. So we rescale it a bit. The other would be to go fully Bayesian and say, given a certain prior assumption of how the distribution should look like, which discounts the extremes, which kind of distribution can we assume under this? I'll point you to some papers doing that, but we're going to keep it simple for the sake of your mental sanity and the portfolio assignment. What about, so n red out of 8 balls? 0 red is low evidence for red. 8 red is high evidence for red. Self is equal red plus 1 divided 10. So we rescale it on a 0 to 1 scale, but we make sure to stay away from 0 and 1. Because 0 plus 1 is 1 divided 10, it becomes 0.1. 8 plus 1 is 9, divided 10 becomes 0.9. And all the numbers in between are going to be equally distributed on that scale. Does that make sense? It's a very small trick, right? Akin to reparameterization, right? That brings us in a space that's nice to deal with. Right? Plus 1 and divided 10 take us away from certainty. Because if you're absolutely certain that there cannot be a single red marble in this urn, then all of your calculations are going to be dragged into that attractor space, into that singularity, into that minus infinite. We can do the same for others, right? But we only have 4 levels. So we could do other plus 1 divided 6, for instance. What if we have a different kind of experiment? In this case, this is the imitation inhibition task, where you see, so you get given instructions. You will see on the screen a red dot. When you see the red dot, raise your middle finger. You might also see a purple dot. When you see a purple dot, raise your index finger. Now on the screen, it's not going to be only the purple or the red dot, but there's also going to be a hand. And that hand might be doing the action that you also need to do, congruence situation, or the opposite, incongruent. What we can use these paradigms to do is to look at how much the social information leaks into your own decision, even when you're explicitly instructed not to do that. You might become, accuracy is only partially impacted, but the reaction time is actually quite strongly affected. Where if you see the hand doing the right move, it will speed you up very much, and it will slow you down very much if you see the opposite action. And actually, a few years ago, we ran these during intro week, and people vary really a lot in how much they're affected by this, which is quite interesting. And there's a million different control conditions to make sure that it's actually the hand and not movement in that specific area. So they mirror flip the hand, or they're put like blocks that appear and stuff like that. So here we have the outcome is again a binomial, middle finger or index finger, right? That's your choice. And we have 2 sources of information, the dot and the hand. So we could say that I can't remember now which one is which, but if the dot is red, purple, no, red, yes. We're going to say that the value is 0.1. That is more evidence towards having to raise the middle finger. If the dot is red, we're going to say that it's going to be, I can't remember which one is which, but there's 2 possibilities. One says middle, the other says index. And we're going to give 0.1 and 0.9, so it's not completely certain. And for the hand, we do the same, right? If it's raising the middle, then it's 0.1. If it's raising the index, then it's 0.9. Does that make sense? That allows us to model this paradigm using the same model. Is it the best way of modeling these data? Well, we could simply just model it as a logistic regression with binary predictors. But if we're starting from having the same model that could apply to a wide variety of domains, and we can start modeling whether these weights for social information are actually the same weight across domains or different weights. So whether there is a constant latent variable underlying, then having the same form, is both intellectually satisfying, but it also useful for the estimation process. Does that make sense? No model is true. Some models are useful, right? Depending on the context, different models are going to be useful. What if the outcome is the reaction time, where we've seen that most people have variations due to this experiment? That's more tricky, right? So there's many fancy ways of doing that, but an easy way of doing that is you invert the RT so that the slowest is close to 0. And then index choice puts a plus sign on it. Middle choice puts a minus sign on it, so that you have a bunch of reaction times which get split in two according to the choice that the person has made. Right? And the slowest reaction times are remapped onto 0 because it's the most uncertain choice. And the fastest reaction times are remapped onto the extreme because they're the most confident choice. Right? And then you can use this to map, map how to say, a wide variety of tasks in which you don't just have the accuracy or the specific choice, but you also have the reaction time to get more information out of that. Okay, so we've seen how we can go from Bayes' theorem to simple Bayes, making some assumptions, and from simple Bayes to weighted Bayes, based on our experience on logistic models. Right? And we've seen how it can be applied to these paradigm, the Gamble task, which has 5 scale predictors and 2 weights. Or to these paradigm, the imitation inhibition, where we have a binomial outcome or rescale reaction time outcome, 2 predictors and 2 weights. And the assignment is going to be applying it to yet another paradigm in which you are shown a phase and you're asked how trustworthy this phase is. And you have a value from 1 to 8. You go through, depending on the paradigm, but I think it's about 150 in the data set that you can access. And after each of your ratings, you get told what your peers have picked. Then you do a filler task for about an hour. Then you're shown again the same 150 phases plus some additional ones. No, it's actually, no. That's actually the same ones in a randomized order. And then you have to rate them again. And the idea is to figure out whether the peer rating that you've received, that was, of course, computerized and made so that for each rating that you give, you get all the other possible deviations, higher or lower, much higher, much lower, just a little higher, just a little lower, influence your rating. And the task is to reconceptualize it as a weighted Bayes. I'll just mention that there's some alternative approaches. So more fancy, but harder to generalize across context because it's really about visual perception and certain forms of action in that handbook. There is another handbook called Probabilistic Models of Cognition, which is really focused on reconstructing the underlying distribution of rate and not conflating it to a single point-wise value, as we've done. By Noah Goodman, Joshua Tenbaum, and a bunch of other people. And actually, Noah Goodman used to be data science lead at Uber. I remember when I visited the building where his lab was, it was California, right? The Bay Area. And he was walking with this linen, almost tunic, with his long curly hair. bare feet in like this very fancy department, and it was very weird. But he's super smart, and he has these, even he made his own probabilistic programming language called Web Probabilistic Programming Language, which does a lot of the things that we've been doing, but in JavaScript, basically. And it can run in relatively fast ways. And this kind of approach has also been recently applied in a really, really cool paper on how not only learners try to combine their experience with what the teacher says, but actually teachers try to infer what the distribution and experience of the students is and adjust their instructions so that they're not communicating the truth, but they're leading the students to infer the truth, right? So if the student is biased, the teacher will also give a biased instruction, but in the opposite direction to compensate for the bias. And that that paper is really good because it both does the agent-based simulation of this to explore how it works, but also can have participant playing the students with agent teachers as teachers with agent students, or against other participants, and show where all the assumptions of the model hold and where they don't hold. Good. We have the whole of 10 minutes to code. We're going to code the first experiment that I showed you, the 4 people and the single sampling of the urn, right? We'll start with just generating 2 for simplicity, right? One other and one self. And what we do is we create a simple Bayes agent, which, because I'm like that, I thought it was a good idea at that time. It's not just the simple Bayes, but also as a bias parameter. And it takes the 2 sources of information and the value for the bias as arguments. And then it's really the outcome is bias plus logit scale of the first source plus logit scale of the second source, right? Nothing new compared to what we're used to. We can fix bias at 0. We can say there's 10 trials, independent the one from the other. We can say that source 1 will give a sequence of values between 0 and 1. Yeah, it steps by 0.1. Between 0.1 and 0.9, actually, a steps of 0.1. Source 2 will do the same. So we have all the possible combinations. We expand the grid, right? So that we have 10 trials for each combination of the values in the 2 sources. So we can explore how the model predicts the belief to change in the agent. And then for each row in the expanded grid, we apply simple Bayes. And then we also apply a decision rule, which in this case is simply a binomial, where we sample 1 trial 1 time from the estimate that the model has created, right? So that we have both an outcome in terms of the rate, but also an outcome in terms of 0 and 1s. Because in the true data, we will not have the belief of the participants, but only their choices. All right. So we look at the distribution of beliefs across all of these possibilities, and we get something that's roughly flat, right? We didn't run 1 million trials, so it's not going to be perfectly flat, but it's going to be roughly flat. Then we look as a function of source 1, the evidence in my own sampling, how much my belief that the next choice should be red changes. We can see that in general, as the evidence in source 1 increases, my belief in red increases, but its price moderated by source 2, by what the other is saying. If the other is very confident that it's going to be red, right, the curve starts very high. If the other is very confident it's going to be green, the curve starts very low. Why is it curved? Why don't we have a bunch of straight lines? Because we do the estimation in log odds and then turn it back into probabilities, which means that the extremes are discounted, or you need to move a lot in log odd space at the extremes to move even a tiny bit in probability space. That's where the spaces worked. But it makes sense because you might not want to be exactly sure of green, right? You might always leave some probability open for red, and vice versa. Stand model is we have a data block, right? Where we have an N of trials at the top, the actual choices of the agent as an array of length N, and then the predictors, right? The input that the agent gets, which is an array of length N for source 1, and an array of length N for source 2. We can then transform the data to have the logit version of the information sources if we haven't done it outside of R. We have the parameters, which in this case is only a bias parameter, and that explains why I put bias in. That is, if you don't have any parameter, you need to do a twist to make stand to fit the data anyway, and this is just easier. We have a model with a prior on bias. It's our normal distribution, center at 0, standard deviation of 1. And we have the model where y is a function of a theta in a Bernoulli distribution, which is bias plus the logit of source 1 plus the logit of source 2. Does that make sense? It's nothing new compared to what we've seen. And then here we generate some quantities, but we don't need to go through that now. We fit the model. We get an ELPD that is a weird measure of how well it fits the data, which we will then use at a later stage when we add a second model. We check the Markov chains. Here we caterpillars. We check the prior posterior update. It's not perfect, but it seems to work. We check the it's called the output. We have the log posterior probability. We have the estimates for bias. We have the prior for bias. All looks decent. Our head is 1 quantitative measure of how well they overlap. The effective sample size is several thousands, so we shouldn't worry about that. Then we do the weighted Bayes. Right. And I'm going to move that because I can't read. In the literature, we have that a 0.5 weight has no impact. A weight of 1 is taking the information at face value. In the model that we had coded, we had a 0 weight had no impact, and a 1 weight was the taking the source of information at face value. So we'll need to do a twist if we want to keep our results compatible with the literature. So we can say that weight 1 minus 0.5 times 2 will go from 0.1 to 1 to a 0 to 1 weight. It's just a simple mathematical transformation. We can discuss it more tomorrow. The function takes a bias, the evidence from source 1, the evidence from source 2, the weight for source 1, the weight for source 2. And then the outcome is generated with the usual equation, right? Bias plus weight 1 times the log odds of source 1 plus weight 2 times the log odds of source 2. When we run the simulation now, we don't just have bias and source as before. We also have different possible values for weights. From 0.5 to 1, because we want to use the literature, relate our results to the literature. We expand the grid, and then for each row in all of these combinations, we're running the weighted base, which generates a belief in the or rate of choosing red, and an actual binary, which is the choice that is made sampling from a binomial distribution using that rate. Yes. And here is what we see. That as we vary the weight of the different sources, we vary how much they impact not only the belief, but also the interpretation of the other. So here, where we value both of them, nothing, 0.5, belief doesn't change as the evidence changes. Here, where we take the two sources at face value, we get exactly the picture as before. In between, what we see is that, for instance, here, we don't take, I think this is weight 2, in any consideration. So there is no variation in how source 1 affects us, depending on what source 2 does, because source 2 is ignored. And all the intermediate stuff. And then here, the only change that we have compared to before is we add the two parameters, weight 1 and weight 2. We transform the parameter to have that 0 to 0.5 to 1 scale. And we add the priors for the two weights. Does that make sense? But tomorrow we'll take some time to describe this. Yes. And with that, we can stop.